Hello, this is Xianghe Dai from University of Bradford. Today I will present our research on numerical study of composite steel cellular beam system using demountable shear collectors. Okay, this presentation will cover introduction, experimental briefing, FE modeling, and validation, parametric study, and conclusion. As you know, currently composite beam systems are extensively used in construction practice. However, the traditional composite system use the shear collector welded on the top flagell of the steel beam. This makes the dismantlement in the future impossible, also make the reuse of the structure member impossible after the building reached its design life. So the demountable shear collector will be a development for shear collection. Okay, a research project carried out in the University of Bradford. We use the cellular beam. We use the demountable shear collector. Okay, the composite beam system is 11.2 meter length, 2.8 wide, slab depth 150 millimeter, and the cellular beam depth 427. The top T of the steel beam is universal beam, and also the bottom T we used for the cellular beam is the universal collar. So, the flagell area ratio of the bottom beam to the bottom flagell to the top flagell is 2.4. The shear collector we used is grade 8.8 and 20 board. Close to the end of the composite beam, then the shear collector spacing is 300. Close to the mid of the composite beam, the shear collector spacing is 600. The shear collector was embedded in the slab 120 millimeter. Okay, and the concrete slab, the material grade is C3037. The tested strength of the concrete is about 40 Newton per millimeter square. Okay. The degree of the shear collection was 38%. This is a little bit less than the requirement based on the Eurocode 4. Okay, and the FE model, and the FE model is shown here. Concrete slab, concrete decker, steel decker profile, and steel mesh and cellular beam, and also the mid-edge train also included in the FE model. So here show you the boundary condition. In order to save computation time and make the modeling easy, we just use half of the structure in the modeling. So you can see the mid-span symmetry here, and the loading position, and also the end support. Okay, and this is the concrete model we used in the FE model for the composite beam system. Okay, as you know, the cubic concrete strength is 40 megapascals. So we take the 32 as the cylinder strength of the concrete. So shear collector behavior, because we didn't model the shear collector, the board as solid element. So we just use the connection element available in the abacus to simulate the shear collector. So based on the test, the push-off test carried out in the University of Bradford, we developed 3 different shear collector models for the composite system. So the first, this A, represent the inner curve. And also the second represent the average curve. And the third one represent the average curve, but remove the slip from here to here caused by the gap between the shear starter and the hole. Okay, here show a comparison of the load to the mid-span deflection. You can see very good agreement achieved if we use the shear collector ABC, but the C is the best one. If we remove the gap between the shear collector and the hole. Okay, from here we also consider the full connection and no connection. You can see the difference. Okay, this figure shows you the comparison between the end slip. Okay, you can see very good agreement achieved. Okay, this figure shows you the loading and the mid-span strain relationship. So also very good agreement achieved. This figure shows you the stress distribution. Okay, you can see compress in the top flagey and tension at the bottom flagey. Okay, before we conducted the parametric study for the concrete strands, we here show you 5 different connection model using different concrete strands, 24, 20, 30, 40, 50, 60. Okay, so here is the comparison using different concrete strands. You can see the higher the concrete strands, the higher capacity, and of course the lower slip. Okay, in the parametric study, we also consider 5 different shear collector arrangement. So 4 of them at the end of the composite beam, we use pair of shear collector, but close to the center of the beam, we use less shear collector. But this case is different. The arrangement of the shear collector at close to the end and close to the center of the composite beam are the same. So here, compare the effect of the shear collector arrangement to the composite beam performance. So the case 4, this case got the highest capacity. Of course, and the shear collector arrangement affected the behavior, the end slip, and also the capacity of the composite beam system. Okay, we also had a parametric study on the symmetry ratio. So the bottom flagey to the top flagey air variation from 1 to 3.5 considered. Okay, this slide shows the effect of the bottom flagellation to the top flagellation to the composite beam performance. You can see some difference here from the capacity. The correlation is not very evident. Okay, the conclusion. First, the FE model developed or validated against the experimental study. So very good agreement achieved. So the FE model developed as an Abacus software could be used to simulate the structure behavior of the composite beam, include the bearing capacity, deflection, slip behavior, and the phase model. And the second point, the higher the concrete strength, the higher the composite beam stiff and load capacity. The lower concrete strength, such as C20-25 concrete, might not allow the steel section to develop full loading capacity due to the shear collection failure. Thus, for the true steel section, the concrete grade should not be lower than C30-37. Okay, the third point, the shear collector arrangement affected the composite beam's behavior. Shear collector close to the beam end contribute more shear resistance to the composite beam system due to the occurrence of higher slip close to end, and thus pairs of shear collector are recommended. The last point, the increasing of the asymmetry ratio increased the end slip due to the neutral axis move down to the beam bottom flagellation. No clear correlation was found between the asymmetry ratio and the composite beam stiffness or loading capacity. However, it appeared that increasing the fragile thickness slightly increased the load capacity of the composite beam system due to the total beam section area increasing. Okay, finally, thanks to the funding from the European Commission and also thanks to the joint project partner, and finally thanks to the technician in the University of Bradford. Thank you for attendance.